Mercury is the closest planet to the Sun, and it is still one of the most surprising. At first glance, it seems simple: a small rocky world, no thick atmosphere, no clouds, almost no tilt, so seasons barely exist, just exposed ground under extreme sunlight. But the closer we look, the less Mercury behaves the way a planet its size should. During the day, temperatures rise high enough to melt lead. At night, they drop hundreds of degrees below freezing. There is no air to hold heat in place, so the surface swings between extremes, and time behaves differently here. One sunrise to the next lasts longer than a full Mercury year. Sunlight can hang in the same sky for a very long time, then disappear into an equally long night. In some regions, the sun does not even move the way you would expect. Its path can slow and reverse because Mercury rotates and orbits in an unusual rhythm. Then there is the part most people never hear about. Near Mercury's poles are craters that never receive direct sunlight. Inside them, water ice can survive for incredibly long periods, protected in permanent shadow on a planet closer to the sun than any other. Beneath the surface, Mercury holds even more surprises. Despite its small size, it has an unusually large metal core, which makes it extremely dense. That core helps generate a magnetic field, something scientists did not expect a planet this small to keep for so long. As the planet cools, its surface slowly contracts. Huge cliffs, hundreds of kilometers long, formed as Mercury shrank and the crust broke and shifted. By the usual rules, Mercury should have cooled, quieted, and faded early in the solar system's history. Instead, it endured, which raises a deeper set of questions. Why is Mercury so dense compared to other rocky worlds? How can ice remain stable on a planet so close to the Sun? What allows a small planet to maintain a magnetic field for so long? And what does Mercury tell us about how rocky planets survive at the edge of what seems possible? Tonight, we travel to Mercury and trace how a small planet survives conditions that should have ended it. But before we begin, I would love to know in the comments where you are listening from and what me is it over there. I love seeing how far these science explorations travel. Now take a slow, deep breath. Let your shoulders relax, and together let us step softly to Mercury and witness the limits of planetary endurance. Mercury moves through space with a quiet speed that is easy to overlook. Its orbit is compact and tightly bound to the Sun, tracing a narrow path that completes itself far more quickly than any other planet. While the outer worlds drift along broad, patient arcs, Mercury's circles close, returning again and again to the same fierce neighborhood. This motion places it in constant proximity to intense gravity and radiation, shaping its journey long before sunlight ever touches the ground. The rhythm of its path sets the tempo for everything that follows. The closeness to the Sun compresses distance into consequence. On Mercury, a small step in location can mean a large change in conditions. Sunlight grows stronger over short spans of space, shadows deepen quickly, and surface temperatures respond with sharp contrast. Unlike planets farther out, where atmosphere and distance soften transitions, Mercury offers little buffer. The environment responds immediately, as if every meter matters. The solar system here feels tightened, drawn inward, with no room for gradual change. Yet proximity alone does not explain Mercury's nature. If closeness were the only factor, Venus would share the same fate, and it does not. Venus sits farther out, wrapped in a dense atmosphere that traps heat and smooths extremes into a heavy stillness. Earth, positioned farther still, carries oceans, weather, and a layered atmosphere that spreads energy gently across its surface. Mars, colder and smaller, lost much of its early air and cooled into a quieter world. Each planet responds differently, even when built from similar rocky beginnings. Mercury's difference lies in how little stands between it and space. Its minimal atmosphere offers almost no protection or redistribution of energy. Without a blanket of air, sunlight strikes directly and escapes just as freely. Heat does not linger, and cold is never held back. The surface reacts instantly to orbital motion, rotation, and shadow. This openness allows external forces to leave clear marks, from solar particles brushing atoms away to impacts preserved without erosion. The planet remains exposed, reactive, and honest about its surroundings. Among the rocky planets, Mercury occupies an edge position, not only in distance but in behavior. It lacks the thick skies of Venus, the stabilizing systems of Earth, and the fated balance of Mars. Its orbit draws it into extremes, but its structure and composition decide how those extremes unfold. Mercury does not fit neatly into patterns shaped elsewhere. It exists as a boundary world, shaped by closeness, yet defined by more than distance alone, quietly reminding the solar system that position sets the stage, but nature still writes its own outcomes. Time on Mercury unfolds in a way that feels detached from instinct. The planet moves swiftly along its narrow path, circling the sun with a pace that leaves other worlds behind. In just 88 Earth days, it completes an entire orbit, slipping around the star before most planets have shifted much at all. This rapid journey gives Mercury the shortest year in the solar system, a calendar measured not in seasons or cycles, but in quick returns to the same fierce closeness. While its path around the sun is fast, Mercury itself turns with remarkable patience. The planet rotates slowly, carrying its surface through space at a measured, deliberate rate. One full spin takes far longer than its swift orbit suggests. This imbalance creates a strange relationship between movement and stillness, where the planet races forward while its ground lingers beneath the light. The surface does not hurry to follow the sky, and in that delay, time begins to fold in on itself. Because of this mismatch, the sun behaves in unfamiliar ways above Mercury's landscape. From certain locations, sunlight climbs into the sky, pauses, and drifts backward before continuing its climb once more. This motion is not an illusion or a trick of terrain, but the result of two rhythms interfering gently with each other. Mercury's orbit carries it forward faster than its rotation can turn away, allowing the sun to reclaim ground it seemed to surrender. Daylight stretches, hesitates, and reshapes itself without urgency. A single cycle from one sunrise to the next lasts far longer than Mercury's year. The planet must complete multiple orbits before the sun finally returns to the same place in the sky. Time here is not counted by how often Mercury circles the sun, but by how slowly its surface rotates beneath that motion. Days become vast spans, stitched together from repeated passes and lingering light, followed by equally long intervals of darkness that arrive with quiet certainty. This unusual balance sets Mercury apart from every other planet. Elsewhere, rotation and orbit settle into familiar ratios that feel natural and predictable. On Mercury, the two motions are locked into a rare harmony, precise and unyielding. The result is a world where years pass quickly, days unfold slowly, and the sun refuses to follow a simple path. Time does not flow in straight lines here. It curves, overlaps, and repeats, leaving Mercury suspended in a rhythm that belongs to no other place, steady in its strangeness and faithful only to its own quiet geometry. On Mercury, the passing of a day cannot be sensed by simple movement of light across the ground. Time unfolds through overlapping motions, layered so tightly that they blur into one another. The planet turns on its axis with steady slowness, completing a full rotation over many Earth weeks. This measured spin is the sidereal rhythm, the quiet turning of Mercury beneath the stars, indifferent to where the sun happens to be. At the same time, Mercury is traveling rapidly along its orbit, carried forward by the Sun's immense gravity. Each lap around the Sun finishes quickly, long before the planet has rotated very far. Because both motions happen together, the surface never experiences day and night in the way most worlds do. The Sun's position in the sky depends not only on Mercury's rotation, but on how far it has moved along its path. These two motions overlap and interfere, stretching time into unfamiliar shapes. A solar day on Mercury, measured from one sunrise to the next, becomes something much larger. The planet must nearly complete two full orbits before the Sun returns to the same place overhead. In that span, Mercury has rushed around the Sun again and again, while its surface continues its patient turn. The result is a single day that lasts longer than a year, a reversal that quietly defies expectation. The Sun's influence reaches deeper than light alone. Mercury is not fully locked to the Sun, but it is held in a delicate gravitational relationship that shapes its spin. The Sun pulls unevenly on the planet's slightly elongated shape, guiding its rotation into a stable pattern. This resonance keeps Mercury's rotation and orbit in a fixed ratio, precise and enduring. Over immense stretches of time, this balance has remained, reinforcing the same extended days and nights without variation. Under this arrangement, sunlight settles in place for long periods. For weeks, the same regions endure relentless illumination, absorbing heat with little pause. The ground warms steadily, not from sudden exposure, but from prolonged contact. There is no swift dusk to offer relief. Heat accumulates slowly, soaking into the surface layers until rock and soil reach their limits. When night finally arrives, it arrives just as patiently. Darkness remains for equally long spans, and with no atmosphere to store warmth, the surface releases its heat back into space. Cooling is gradual but unprotected, and temperatures fall steadily into deep cold. The land experiences extremes not because of violent change, but because change comes so slowly and lasts so long. This rhythm defines daily life on Mercury, though nothing living marks its passage. Days are vast intervals of endurance, shaped by geometry and gravity rather than clocks or seasons. Time here is not hurried or gentle. It simply persists, unfolding according to rules written by motion and mass, repeating the same long pattern beneath the steady pull of the Sun. Heat on Mercury is not delivered in flashes or bursts. It arrives gradually, carried by long exposure rather than sudden intensity. When sunlight settles over the surface, it remains there for extended periods, allowing energy to build without interruption. Rock absorbs this radiation steadily, layer by layer, until temperatures climb high enough to soften metals that remain solid elsewhere. Lead would not hold its shape here. The surface does not flare or glow. It simply grows hotter as time passes, responding patiently to the Sun's presence. This heat is not distributed or shared. Mercury lacks a substantial atmosphere, and without that envelope, there is nothing to move warmth from one place to another. On planets with thick air, winds blur boundaries, carrying energy across continents and oceans. On Mercury, each region stands alone. Sunlit ground heats in isolation, with no current to carry warmth away. Shadows offer sharp relief, not gradual change, and the surface responds immediately to where light does and does not fall. As daylight stretches on, the ground continues to warm, not because the Sun grows stronger, but because it refuses to leave. Slow rotation keeps the same areas facing the Sun for weeks at a time. Heat accumulates not from violence, but from persistence. Stones and dust reach extreme temperatures through endurance rather than force, storing energy until they can hold no more. The landscape becomes a record of exposure, shaped by how long it remains illuminated rather than how brightly it shines. When night finally comes, the reversal is just as extreme. Without an atmosphere to trap warmth, Mercury releases its stored heat directly into space. Cooling begins immediately and continues without resistance. The same slow rotation that allowed heat to build now allows cold to deepen. Darkness lasts long enough for surface temperatures to fall far below anything experienced on Earth. Even carbon dioxide can freeze in these conditions, not because Mercury is distant from the Sun, but because its nights are long and unguarded. The transition between these extremes is not gentle. There is no lingering twilight moderated by air, no gradual shift softened by clouds or weather. Temperature follows time with strict obedience. Prolonged sunlight brings prolonged heat. Extended darkness brings extended cold. The surface expands and contracts through these cycles, responding physically to the rise and fall of thermal stress, though those changes unfold slowly across immense spans. Mercury's temperature extremes are not defined by chaos, but by clarity. Every factor plays its role without interference. Thin air offers no protection. Slow rotation offers no relief. Distance from the sun explains only part of the story. What remains is a world where heat and cold take turns, shaping the surface with patience, each waiting its long season to return, unchanged, predictable, and severe. Mercury does not wear a sky in any familiar sense. Above its surface, there is no layered blanket of air drifting, circulating, or settling into weather. Instead, space presses almost all the way down to the ground. The planet's gravity is weak compared to larger worlds, and its closeness to the sun exposes it to constant energetic forces. Together, these conditions make it difficult for Mercury to hold on to gases for long. Anything light enough to rise is easily encouraged to leave. Over time, whatever gases once lingered were slowly stripped away. Fast-moving particles from the sun collide with atoms near the surface, transferring energy that sends them outward. Heat adds to this loss, giving atoms the speed they need to escape Mercury's grasp. Without the mass to pull them back, or the distance to shield them, the planet remains exposed. Retention never becomes accumulation, and accumulation never becomes permanence. What remains is something far thinner than an atmosphere. Mercury possesses an exosphere, a sparse collection of atoms that barely interact with one another. Unlike an atmosphere, where gases mix, collide, and flow as a system, an exosphere is closer to a ghostly presence. Individual atoms follow their own paths, rising and falling in slow arcs before returning to the surface or drifting away entirely. There are no winds here, no pressure, no continuous layer of air. The exosphere is constantly changing because it is constantly being replenished and erased. Atoms are knocked free from the surface by solar radiation, a process where sunlight itself provides the energy needed for release. Others are ejected when tiny micrometeorites strike the ground, vaporizing small patches of rock and dust on impact. Each collision lifts fresh material upward, briefly adding to the surrounding cloud before it thins again. This exchange happens without pause. Atoms rise, hover briefly, then vanish into space or settle back down. Some are pushed away by the solar wind, swept outward by streams of charged particles flowing from the sun. Others fall back, only to be liberated again later. The exosphere never stabilizes or grows thick. It exists in a delicate balance between loss and replacement, shaped by constant interaction with its environment. Because there is no true atmosphere, Mercury's surface remains directly connected to space. Sunlight reaches the ground without diffusion, and heat escapes without resistance. Impacts leave sharp scars that are never softened by wind or rain. Chemical traces remain close to where they form, recorded in the surface itself rather than carried elsewhere. The planet's outermost layer tells its story plainly. Mercury's absent atmosphere is not an emptiness, but a condition. It reflects a world where gravity, distance, and solar influence align in a way that prevents shelter from ever forming. What exists instead is a fragile veil, endlessly renewed and endlessly lost, hovering briefly above a surface that remains fully exposed to the long history of space. Mercury's surface rests in a state of long remembrance. Across its plains and highlands, circular scars overlap and crowd together, each one marking a moment when space reached down and struck solid ground. Craters vary in size and age, some sharp and well defined, others softened only by time itself. They do not fade into one another gently. Instead, they stack, interrupt, and persist, forming a landscape shaped far more by collision than by renewal. What is absent here is as important as what remains. There is no rain to wear down edges, no wind to carry dust from one place to another, no flowing water to soften the land. Mercury has no weather systems to blur its features, and no thick atmosphere to erode exposed rock. Once an impact reshapes the surface, there are few forces left to undo the change. The planet's face keeps what it is given. Mercury also lacks the internal movements that quietly reshape other rocky worlds. There are no shifting plates sliding past one another, no slow recycling of crust back into the interior. The surface does not renew itself through large-scale motion. Instead, it remains mostly fixed, adjusted only by rare volcanic flooding early in its history and by the steady accumulation of impacts afterward. Change here is infrequent and incomplete. Because of this stillness, ancient features remain visible far beyond their expected lifetimes. Craters formed billions of years ago sit beside younger ones, their boundaries still readable despite immense age. Even delicate patterns of ejecta and fractured rims linger. The ground does not forget easily. Each mark stays where it was made, preserved with minimal alteration, turning the surface into a layered archive rather than a living landscape. As impacts accumulated, Mercury's surface gradually became a record of the solar system's youth. During its earliest eras, debris was more abundant and collisions were more frequent. The heavy cratering reflects that violent beginning, capturing an era when planets were still forming and stabilizing. While other worlds have erased much of that evidence through erosion or tectonic renewal, Mercury kept it intact. This preservation allows scientists to read time directly from the ground. By comparing crater densities and overlap, relative ages emerge, revealing which regions formed first and which arrived later. The surface functions like a chronicle written in stone, where events are not described but embedded. Each impact adds a line, each quiet interval leaves a space. Mercury's frozen surface does not suggest inactivity. Instead, it reflects endurance. The planet has remained exposed long enough for its earliest memories to stay visible. Its terrain speaks in accumulated moments rather than continuous motion. In doing so, Mercury becomes more than a place of extremes. It becomes a keeper of origins, holding on to a version of the solar system that has vanished everywhere else, preserved not by care or protection, but by the simple absence of change. Long before Mercury settled into its present stillness, it endured an age of repeated disruption. In that distant era, the young solar system was crowded and unstable, filled with fragments moving along intersecting paths. Mercury's position placed it directly in the flow of this debris. Impacts were not rare events, but recurring interruptions, arriving from many directions with little warning. The planet absorbed these encounters without the protection of thick air or distance. Some of the collisions were immense. Vast impact basins spread across the surface, their rims stretching hundreds of kilometers from their centers. These basins did not simply dent the crust, they reshaped it. The force of impact fractured rock deep below the surface, thinning and weakening the crust in wide regions. Melted materials surged outward and settled again, altering the surrounding terrain in ways that still remain visible today. These events marked turning points rather than isolated scars. Each large collision added stress to a crust already forming under extreme conditions. Shock waves traveled through the planet's outer layers, rearranging minerals and altering the structure of the ground. In places, fractures extended far beyond the original impact site, linking distant regions through invisible lines of stress. Mercury's crust became a mosaic assembled through force, its shape influenced as much by violence as by slow cooling. Over time, smaller impacts continued to arrive, layering new craters across older ones. The density of these marks became a quiet measure of age. Regions with heavy cratering reflect surfaces that have remained unchanged since the earliest periods of planetary formation. Where craters overlap and crowd together, the surface speaks of ancient exposure. Areas with fewer marks suggest later modification or resurfacing. Brief intervals when molten rock smoothed the ground before impacts resumed. By comparing these densities across the planet, scientists trace Mercury's timeline. The surface records not only the frequency of impacts, but the gradual decline of chaos in the solar system. Early on, collisions were constant and severe. As time passed, debris thinned and the pace slowed. Mercury's battered appearance preserves that transition with unusual clarity, capturing both the intensity of the beginning and the gradual settling that followed. Mercury appears unusually scarred because it kept what others lost. Larger planets erased their early damage through erosion, tectonics, or atmospheric processes. Mercury had none of these tools. Its surface remained exposed, and its interior offered little means of renewal after its early volcanic phase faded. Each impact remained, preserved by stillness rather than reinforced by change. The planet's violent beginning is not a contradiction of its quiet present, but its foundation. Mercury carries the memory of a time when survival required endurance rather than adaptation. Its surface holds the imprint of that era without commentary or embellishment. In the silence of its craters and basins, the planet records a history shaped by collision, one that unfolded not through dramatic endings, but through accumulation, persistence, and the gradual fading of chaos into order. Deep beneath Mercury's silent surface lies a structure that quietly sets it apart. The planet's interior is dominated by metal, to an extent unseen among the other rocky worlds. Its core occupies an unusually large fraction of its total volume, leaving far less room for the rocky mantle that typically surrounds such hearts. This hidden imbalance shapes Mercury from the inside outward, influencing its density, gravity, and long-term behavior. When compared to Earth, the difference becomes clear. Earth's iron-rich core is substantial, yet it is wrapped in a thick mantle of rock that accounts for much of the planet's size. Venus and Mars follow similar patterns, with broad rocky layers separating their surfaces from their metallic centers. Mercury does not. Its core reaches outward, far closer to the surface, compressing the mantle into a comparatively thin shell. The planet feels heavy for its size because so much of it is metal. Measurements of Mercury's mass and radius reveal this interior truth without direct access. Density alone signals that something unusual lies beneath the crust. To match what is observed, models require a core far larger relative to the planet than those of its neighbors. This result has remained consistent across decades of study, reinforcing the idea that Mercury formed or evolved under conditions different from the rest of the inner solar system. The question is not whether Mercury's core is oversized, but how it became that way. One possibility traces back to the earliest stages of planetary formation, when material near the Sun experienced extreme temperatures. Lighter rocky components may have been lost more easily, either vaporized by heat or prevented from fully accreting. In this view, Mercury formed already biased toward metal, its mantle never allowed to grow thick in the first place. Another explanation considers violent early events. Large impacts during the chaotic youth of the solar system could have stripped away portions of Mercury's rocky exterior. Repeated collisions may have removed mantle material while leaving the dense core largely intact. Over time, this process would exaggerate the planet's metal dominance, reshaping its internal proportions without altering its orbital position. A third line of thought focuses on chemical conditions rather than force. Mercury appears to have formed in an environment richer in metal and poorer in oxygen than that of Earth. Under such circumstances, more iron would remain metallic rather than binding into rocky minerals. This chemistry would naturally favor a larger core without requiring unusual impacts or losses. Each of these explanations remains grounded in known processes, and none relies on speculation beyond physical evidence. What they share is an acknowledgement that Mercury occupies an extreme position in planetary formation outcomes. Its giant core is not an anomaly without cause, but a result shaped by heat, timing, and material availability. The planet's interior tells a quiet story of constraint and selection, written long before the surface ever recorded its first scar. Metal defines Mercury in a way that is felt rather than seen. Beneath the thin crust and compressed mantle, iron shapes nearly every physical trait the planet displays. The interior is not balanced between rock and metal as it is on other rocky worlds. Instead, metal dominates, forming a vast central mass that governs how Mercury moves, how it responds to gravity, and how it interacts with the space around it. This hidden structure was not revealed through drilling or direct sampling, but through careful measurement. By tracking Mercury's mass and observing how strongly it pulls on nearby spacecraft, scientists determined its density. For a planet of its size, that density is unusually high. Rock alone cannot account for the weight. Only a large concentration of heavy elements can explain the numbers. From this, Mercury's interior takes shape in models as a world where iron fills most of the volume, pressing outward beneath a relatively thin rocky shell. That metal-rich interior affects gravity in subtle but important ways. Mercury's strong gravitational pull for its size influences how material settles across the surface and how the planet responds to external forces. The crust rests closer to the core than on other planets, shortening the distance between surface and metal heart. This proximity allows internal processes to leave clearer imprints, whether through contraction, stress, or magnetic effects. Iron also brings another consequence. Despite Mercury's small size, it possesses a global magnetic field. This field is weaker than Earth's, but its existence is remarkable given the planet's scale and slow rotation. The large iron core plays a central role, allowing electrical currents to flow within partially molten regions. These slow movements generate magnetism that extends into space, shaping how solar particles interact with the planet. This magnetic presence alters Mercury's relationship with the Sun. Charged particles are guided and deflected rather than striking the surface uniformly. While the field offers little protection compared to Earth's, it introduces structure into an otherwise exposed environment. The magnetosphere forms a faint shield, one sustained not by atmospheric layers or size, but by the sheer abundance of metal within. No other rocky planet combines such extreme metal dominance with such small size. Earth, Venus, and Mars all balance their interiors more evenly between rock and iron. Mercury stands apart, not simply heavier, but fundamentally different in construction. Its interior resembles an exposed core more than a layered planet, as though the usual proportions were rearranged early and never corrected. This uniqueness makes Mercury valuable far beyond its orbit. It demonstrates how planetary outcomes can diverge when conditions shift slightly during formation. Metal did not merely settle into Mercury. It claimed the planet. The result is a world where gravity, magnetism, and structure all reflect the same quiet truth. Mercury is not shaped around its metal. It is shaped by it, held together by a core that defines everything above it. Long after Mercury revealed its scars and extremes, it offered another quiet contradiction. As spacecraft passed by and instruments listened closely, traces of magnetism appeared where none had been expected. The planet was interacting with the solar wind in a patterned way, bending charged particles instead of allowing them to strike freely. This behavior signaled the presence of a global magnetic field, faint but unmistakable, surrounding a world thought too small and too slow to sustain one. The discovery surprised scientists because magnetic fields are usually linked to specific conditions. On Earth, magnetism arises from a large, rapidly rotating planet with a substantial molten core. The movement of liquid metal generates electric currents, which in turn create a strong and stable magnetic field. Mercury seemed to lack several of these ingredients. Its small size suggested that its interior should have cooled quickly. Its slow rotation appeared insufficient to drive the necessary internal motion. By established models, Mercury should have been magnetically quiet. Instead, it was not. Measurements showed that Mercury's magnetic field is global, aligned roughly with its rotation axis and persistent. Though weaker than Earth's, it shares key structural traits. It forms a magnetosphere that interacts with the Sun, creating regions where charged particles are guided along invisible lines rather than striking the surface directly. This field is not a temporary effect or a remnant frozen in stone. It is active, generated from within. Compared to Earth's magnetic field, Mercury's is far gentler. It is only a small fraction of Earth's strength and offers limited shielding. Solar particles still reach the surface in many areas, yet the comparison highlights something important. Strength is not the defining feature here. Existence is. For a planet of Mercury's size, any global magnetic field at all is significant. This magnetism suggests that Mercury's interior is not fully solid. Somewhere deep below the surface, part of its metal core must still be molten. Within that liquid layer, slow movements of conductive material create electrical currents. These currents maintain the magnetic field, even if they move at a more measured pace than those within Earth. The planet's large iron core, discussed earlier, plays a central role by retaining heat longer than expected and providing ample conductive material. Mercury's magnetic field also reflects balance rather than intensity. Its rotation and core structure appear locked into a narrow window where magnetism can persist without growing strong. The field is stable but modest, sustained without dramatic fluctuation. It mirrors the planet itself, restrained, enduring, and defined by limits rather than excess. This unexpected magnetism reshapes how Mercury is understood. The planet is not a static relic frozen shortly after formation. Its interior remains subtly active, continuing processes that were assumed to have ended long ago. The magnetic field stands as quiet evidence that Mercury's story did not stop when its surface fell still. Beneath the silence, motion continues, slow and persistent, keeping a small planet alive in ways that challenge simple expectations. Deep inside Mercury, the metal that defines the planet has not settled into complete stillness. Beneath the crust and compressed mantle, the core remains in a state that is neither fully liquid nor entirely solid. This interior condition is inferred not through direct observation, but through subtle signals that rise quietly to the surface and beyond, carried by the planet's magnetic behavior and gravitational response. The presence of a global magnetic field provides the strongest indication. Magnetic fields generated by planetary interiors require motion within electrically conductive material. A fully solid core cannot sustain such movement. The persistence and structure of Mercury's magnetism therefore point to a core that retains at least a portion of molten metal. This molten layer does not need to be vast. Even a thin shell of liquid iron, moving slowly beneath solid layers, is enough to maintain the faint field detected around the planet. Additional clues come from how Mercury responds to external forces. As the planet moves through space, tiny variations in its rotation and orientation can be measured. These variations suggest that the outer shell and the core are not perfectly locked together. A partially molten interior allows the outer layers to shift slightly independently of the deeper metal. This subtle decoupling is consistent with a core that has not fully crystallized. The importance of a small molten region extends beyond magnetism. Liquid metal conducts heat differently than solid material. Its presence allows internal warmth to be redistributed rather than trapped entirely at the center. This slows the cooling process, extending the lifespan of internal activity far beyond what Mercury's size alone would predict. The planet loses heat slowly, not because it is large, but because its composition and structure resist rapid change. Mercury's core is exceptionally rich in iron, and iron holds heat efficiently. Combined with the planet's early formation under extreme conditions, this composition allowed significant warmth to persist deep within. Over billions of years, that heat has diminished, but not vanished. The molten layer remains as a remnant of that earlier intensity, a quiet continuation rather than a vigorous engine. This partial melting reshapes how Mercury's history is understood. The planet is not a fully extinguished world that cooled and fell silent early in the solar system's life. Its interior has followed a slower timeline, governed by metal abundance and constrained heat loss. While its surface bears the marks of long exposure and minimal renewal, the interior tells a different story, one of gradual transition rather than abrupt ending. Mercury's heart reveals that planetary evolution does not proceed at a single pace. Surface stillness does not always reflect internal state. A thin molten layer, hidden far below, carries meaning far larger than its size suggests. It preserves magnetism, regulates cooling, and extends the planet's internal life. In doing so, it reinforces Mercury's place as a world defined not by simplicity, but by endurance, expressed in the smallest remaining motions of its metal core. Mercury's surface carries signs of movement that did not come from impact or eruption. Long cliffs rise abruptly from the ground, stretching across plains and cutting through older terrain without regard for what lay there before. These scarps form step-like edges, where one side of the surface has been lifted above the other. They are found across the planet, not clustered in one region, and their presence tells of a change that affected the entire world at once. These cliffs were discovered through careful mapping of Mercury's surface, as images revealed repeated patterns too extensive to be accidental. They appear as steep walls, sometimes hundreds of meters high, extending for hundreds of kilometers. Unlike craters, they are not circular or centered on a single event. Instead, they trace lines of compression where the crust has been forced to adjust to a shrinking interior. The cause of this reshaping lies deep within the planet. As Mercury's interior slowly cools, its metal-rich core contracts. Cooling reduces volume, and over immense spans of time, even small changes add up. The interior pulls inward, but the rigid crust cannot simply shrink smoothly with it. Instead, stress builds until the surface responds by breaking and shifting. The crust shortens, buckles, and overlaps, creating the cliffs observed today. This process has been gradual rather than sudden. Mercury did not collapse inward in a single moment. It contracted quietly over billions of years, with each increment of cooling adding a little more strain. When the surface could no longer hold that strain evenly, it fractured. The resulting scarps record these adjustments, preserving moments when the planet's outer shell gave way to deeper forces. Measurements of these features allow scientists to estimate how much Mercury has shrunk. By analyzing their height and distribution, researchers conclude that the planet's radius has decreased by several kilometers since its formation. While this change may sound small on a planetary scale, its effects are dramatic at the surface. A reduction of only a few kilometers is enough to force widespread deformation across a world of Mercury's size. As the crust compressed, older features were not erased, but displaced. Cliffs sliced through craters of different ages, confirming that contraction continued long after the period of heavy bombardment ended. The surface became a layered record where impacts and internal changes overlap, each telling a different part of the planet's story. The reshaping did not replace earlier history, it added to it. Mercury's slow shrinking reflects the same endurance seen elsewhere on the planet. Cooling was inevitable, but it did not bring stillness. Instead, it produced motion of a quieter kind, one that altered the surface without violence or speed. The cliffs stand as reminders that even a world long exposed and seemingly static can continue to change from within, guided by heat slowly fading from a dense metal heart. Across Mercury's surface, long fractures stretch beyond the horizon, tracing paths that ignore the shapes beneath them. These faults do not follow the gentle curves of craters or the outlines of ancient plains. They run straight and determined, crossing varied terrain with little deviation, as if the surface itself were folded along invisible seams. Some extend for hundreds, even thousands, of kilometers, linking distant regions through a single line of disruption. Up close, these faults appear as towering scarps, where one block of crust has been thrust upward over another. The ground on one side rises sharply, casting long shadows that emphasize the scale of the displacement. On the other side, the surface drops away, leaving a broken edge where rock once lay continuous. These features do not form isolated ridges. They belong to a global pattern, repeating across the planet in different directions and orientations. Their origin lies in the same slow contraction that reshaped Mercury over time, but their reach reveals something more expansive. As the interior cooled, the planet did not shrink evenly. Stress accumulated along broad zones, where the crust eventually failed along deep, continuous faults. When these breaks occurred, they propagated across great distances, carving through the surface in a way that local impacts never could. The planet adjusted not in small corrections, but in sweeping structural shifts. One of the most revealing aspects of these faults is what they cut through. Craters of many different ages are interrupted and displaced along the same fracture lines. Older, heavily worn craters are split just as cleanly as younger, sharper ones. This overlapping tells a quiet story of timing. The faults did not form during a single ancient episode. They remained active long after the era of heavy bombardment had passed, continuing to reshape the crust as Mercury cooled further. In some places, the faults offset crater rims, lifting one side higher than the other and breaking the circular symmetry that impacts once imposed. Elsewhere, crater floors are tilted or fractured, evidence that the ground moved after the impact scars were already in place. These relationships allow scientists to trace the sequence of events, revealing a surface altered repeatedly by internal forces long after external collisions became rare. The scale and persistence of these fractures point to prolonged cooling rather than sudden collapse. Mercury's interior did not lose heat quickly and catastrophically. It released energy slowly, tightening the planet over immense spans of time. Each increment of cooling added stress, and when the crust could no longer accommodate it, faults extended and deepened. The process repeated, leaving layered evidence of adjustment rather than a single moment of failure. These continent spanning cracks reveal a planet that continued to respond long after its surface appeared quiet. They show that Mercury's history is not divided neatly between early violence and later stillness. Instead, it unfolds as a gradual sequence of internal change, written into the surface through fractures that connect distant places and distant times, all shaped by the steady cooling of a dense, metal-rich world. At Mercury's poles, sunlight behaves differently. The planet's axis tilts only slightly, leaving the sun low on the horizon, even at its highest seasonal reach. In this geometry, some crater interiors never receive direct light. Their floors remain in constant shadow, untouched by sunrise or sunset. While the surrounding surface endures extreme cycles of heat and cold, these pockets remain isolated from change, hidden from the star that dominates the rest of the planet. The existence of these permanently shadowed craters was understood before their contents were known. Their depths and angles create natural cold traps, regions where temperatures remain remarkably stable. Shielded from sunlight and insulated by surrounding rock, these areas can stay colder than almost anywhere else on Mercury. Heat from nearby terrain does not easily reach them, and the absence of atmosphere prevents warm air from drifting inward. Darkness here is not temporary, it is structural. Evidence of ice emerged not through direct images, but through radar observations. When radar signals were sent toward Mercury's poles, some regions reflected the signals unusually well. The pattern of reflection matched what is seen from water ice elsewhere in the solar system. The signals were bright, consistent, and confined precisely to those shadowed areas. The conclusion formed quietly. Beneath the darkness, frozen water was present. For ice to survive so close to the sun, conditions must be exact. Any exposed water would quickly sublimate, escaping into space. Within these shadowed craters, however, temperatures remain low enough for ice to remain stable over immense spans of time. Once delivered, either by comet impacts or water-rich asteroids, the ice would settle into the cold trap and remain. Without sunlight to drive it away, and without atmosphere to redistribute heat, it simply stays. Over billions of years, this process could accumulate significant deposits. Each delivery adds a thin layer, preserved by the same stillness that protects the surface elsewhere. The ice does not melt, flow, or evaporate in any meaningful way. It becomes part of the crater floor, locked in darkness, as the planet around it continues to endure extremes. Time passes without altering these reserves. This discovery reshaped how scientists view the inner solar system. Worlds close to the Sun were once assumed to be uniformly dry, stripped of volatile substances by heat and radiation. Mercury's polar ice demonstrated that distance alone does not determine habitability or retention. Geometry, rotation, and local environment matter just as much. Even in the harshest neighborhoods, stable refuges can exist. The ice on Mercury is not a sign of abundance, but of persistence. It survives not by resisting the sun, but by avoiding it completely. In doing so, Mercury reveals a quiet complexity. The closest planet to the sun is not entirely defined by heat. Within its deepest shadows, it holds cold, ancient water, preserved across epochs, challenging simple divisions between inner and outer worlds, and expanding the idea of where fragile materials can endure. Near Mercury's poles, the sky follows a rule unlike anywhere else on the planet. The sun never climbs high. It traces shallow arcs close to the horizon, skimming the edges of the landscape without ever rising overhead. This behavior is set by Mercury's minimal axial tilt, which keeps the planet upright as it moves around the sun. Seasons barely shift, and the sun's apparent height changes so little that certain places remain untouched by direct light forever. In these polar regions, crater walls rise like barriers against the low-angled sun. Their rims catch what little light arrives, while their interiors fall into shadow. Because the sun never climbs high enough, its rays cannot clear the edges. The geometry is simple and relentless. Once a crater floor falls into shadow, it stays there. Day after day, year after year, the light passes nearby but never enters. This creates regions of permanent darkness, not caused by distance or atmospheric haze, but by orientation alone. These shadows are not fleeting or seasonal. They are fixed features of the landscape, as enduring as the rock that encloses them. While most of Mercury experiences long cycles of glare and darkness, these craters remain locked in night, immune to the planet's broader rhythms. Inside these shadowed spaces, temperature behaves differently. Without sunlight to drive heating, and without an atmosphere to transport warmth from nearby regions, the crater floors remain cold and stable. Temperatures stay remarkably consistent across time, varying little compared to the rest of the planet. Heat from surrounding sunlit ground does not easily penetrate. The darkness acts as insulation, preserving cold rather than allowing extremes. This stability is unusual on a world known for dramatic swings. Elsewhere on Mercury, surfaces expand and contract as temperatures rise and fall. At the poles, within these craters, change slows. Thermal stress becomes minimal. The environment settles into a quiet equilibrium defined by absence rather than exposure. Cold persists not through force, but through exclusion. Sunlight never reaches these regions because Mercury's orientation never allows it. The planet does not tilt enough to bring the sun overhead, even over long spans of time. The slow rotation and stable axial alignment work together, ensuring that the sun's path remains low and predictable. The shadows do not drift or fade. They remain anchored, to the same places across billions of years. These permanently dark craters reveal a different side of Mercury's character. The planet is not shaped solely by extremes of heat and radiation. It is also shaped by precise geometry and stillness. At the poles, darkness becomes a defining feature, carving out environments untouched by the sun. In these quiet hollows, Mercury demonstrates how even the harshest worlds can contain regions governed not by intensity, but by balance and restraint. The presence of water on Mercury points outward rather than inward. The planet itself offers little opportunity for water to form or remain through internal processes. Its heat, exposure, and lack of atmosphere make long-term retention unlikely unless the water arrived already protected. The source is traced not to Mercury's interior, but to countless small visitors that crossed its path over deep time. Comets and certain types of asteroids carry water locked within ice and hydrated minerals. As these bodies move through the inner solar system, some collide with rocky planets. On Mercury, many of these impacts occurred early, when debris was abundant and impacts frequent. Each collision delivered small amounts of volatile material scattered across the surface. Most of it was quickly lost to heat and space, but a fraction migrated toward regions where survival was possible. Isotopic measurements help clarify this origin. By comparing the ratios of hydrogen isotopes associated with Mercury's polar ice to those found in comets and water-rich asteroids, scientists find close similarities. These ratios act like fingerprints, preserving information about where the water formed. The match suggests an external origin, consistent with material delivered from colder regions of the solar system rather than produced locally. Once delivered, water molecules did not remain evenly distributed. Sunlight drove volatile material away from exposed regions, while Mercury's weak gravity allowed much of it to escape entirely. Some molecules, however, traveled across the surface in a slow, unpredictable dance. When they encountered permanently shadowed craters near the poles, movement stopped. The cold trapped them in place, where they accumulated gradually over immense spans. This pattern reflects a process seen across the solar system. Water delivery does not rely on a planet forming in a specific location or having special internal conditions. Instead, it depends on timing, impact history, and the presence of cold traps or protective environments. Earth, Mars, the Moon, and Mercury all show signs of water delivered after formation, carried inward by small bodies shaped far from the Sun. Mercury's ice confirms that proximity does not prevent this exchange. Even close to intense heat, water can arrive, move, and persist under the right circumstances. The solar system operates less like a set of isolated zones and more like a connected environment where material circulates across vast distances. What forms in cold, distant regions can end up preserved on worlds thought too harsh to support it. For other rocky planets, including those beyond the solar system, this has broad meaning. Water does not need to be native to shape a planet's history. It can arrive later, quietly altering surface chemistry and long-term potential. Mercury, often seen as the most stripped and extreme of the rocky worlds, still carries this shared history. Its water is not an exception, but a reminder that even the driest planets participate in the same slow exchange that moves material and possibility throughout planetary systems. Mercury's surface carries a chemical signature that quietly separates it from the other rocky worlds. When spacecraft measured the elements embedded in its crust, the results did not align with expectations shaped by Earth or its neighbors. The ground beneath Mercury's harsh light revealed a composition formed under unusual conditions, preserved by the same stillness that protects its ancient terrain. Instruments detected a mix of elements familiar to planetary science, but in unfamiliar proportions. Iron is abundant in the interior, yet the surface rocks themselves contain surprisingly low amounts of iron bound into minerals. Instead, other elements appear more prominently. Among them, sulfur stands out. Mercury's crust contains far more sulfur than would normally be expected, so close to the Sun, where high temperatures were once thought to drive such volatile elements away. This elevated sulfur content suggests a formation environment unlike Earth's. Sulfur tends to bond with metals and prefers conditions where oxygen is scarce. Mercury appears to have formed in a region of the early solar system that was chemically reducing, meaning there was less free oxygen available. Under these conditions, sulfur remained stable rather than escaping or oxidizing into different compounds. The planet's building materials carried this signature from the beginning. The presence of sulfur also influences how Mercury's crust behaves. Sulfur lowers the melting point of rock, allowing volcanic activity to occur more easily in the planet's early history. It also affects mineral structure, producing surface compositions that differ subtly but meaningfully from those found on Earth. The crust reflects not only what materials were present, but how they combined under extreme heat and low oxygen conditions. Earth's chemistry tells a different story. Our planet formed in a more oxygen-rich environment, allowing iron to oxidize and become locked into silicate minerals. Sulfur on Earth is less dominant at the surface, often buried deeper or incorporated into biological and atmospheric cycles. Plate tectonics, water, and weather continually reshape Earth's chemical record, blending and redistributing elements over time. Mercury lacks these reshaping forces. Its chemistry remains close to its original state, modified only by impacts, limited volcanism, and space weathering. What spacecraft detect today is not a polished outcome of ongoing processes, but a preserved snapshot of early planetary conditions. The crust holds onto its chemical identity with little interference. This unusual chemistry reinforces the idea that Mercury did not simply form as a smaller version of Earth. It emerged from a distinct set of circumstances, shaped by proximity to the Sun, timing within the solar nebula, and the availability of certain elements. Its sulfur-rich surface speaks to a planet assembled where heat was intense but oxygen was limited, and where metal and volatile elements followed different rules. Mercury's composition expands the range of what rocky planets can be. It shows that shared categories do not guarantee shared outcomes. Chemistry, like orbit and interior structure, reflects local history. In Mercury's case, that history is written clearly in stone, unsoftened by later change, offering a rare glimpse into the diversity of planetary beginnings. Mercury's crust took shape under conditions that allowed little room for balance. From the beginning, the planet formed close to intense heat, surrounded by material already altered by proximity to the Sun. As the outer layers cooled and solidified, the crust that emerged reflected a world assembled under pressure rather than moderation. Its structure was thin, tightly bound to the interior below, and shaped by a chemical environment unlike that of other rocky planets. Despite the planet's massive metal core, Mercury's surface rocks contain relatively little iron locked into minerals. This contrast appears counterintuitive at first glance. The explanation lies not in absence, but in separation. Much of Mercury's iron migrated inward during formation, drawn by gravity, while the planet was still hot enough for metals to move freely. What remained at the surface was depleted by comparison, leaving silicate rocks with lower iron content than expected for such a dense world. This separation influenced how the crust responded to internal heat. Early in Mercury's history, residual warmth from formation and radioactive decay allowed molten material to rise from below. Volcanism unfolded quietly and extensively, not through towering cones or explosive eruptions, but through widespread flooding. Lava seeped upward and spread across low-lying regions, filling basins and smoothing older terrain beneath dark, solidifying flows. These volcanic episodes occurred during a limited window. As Mercury lost heat, the capacity for magma generation diminished. The eruptions were not constant, but episodic, shaped by internal chemistry and cooling rate. When they occurred, they altered large portions of the surface at once, creating broad plains rather than isolated features. The lava was fluid, capable of traveling far before settling, indicating low viscosity influenced by composition and temperature. Evidence of these ancient lava plains remains visible today. Smooth expanses interrupt the heavily cratered landscape, their surfaces marked by fewer impacts and different textures. In some regions, volcanic plains bury older craters, preserving only their rims as faint outlines beneath hardened rock. These relationships reveal that volcanism followed much of the early bombardment, adding a second chapter to the planet's surface history. The crust that resulted from these processes became a composite of survival and interruption. It holds scars from impacts, overlays from lava, and stresses imposed by the shrinking interior. Unlike Earth, Mercury never developed plate tectonics to recycle or renew its crust. Once formed, each layer remained largely where it was placed, accumulating history rather than replacing it. This crust tells a story of formation shaped by extremes rather than equilibrium. Mercury did not simply inherit the same crustal processes scaled down in size. It followed a distinct path, guided by metal-rich interiors, reduced chemistry, and rapid early cooling. The surface seen today reflects that difference clearly. It is a crust built quickly, modified briefly, and then left to endure, preserving a record of a planet that formed under conditions few others experienced. On Mercury, traces of fire remain without the machinery that usually sustains it. The planet shows clear signs of ancient volcanic activity, yet it never developed the moving plates that drive volcanism on Earth. There were no shifting boundaries or recycling crust. Instead, Mercury's volcanism rose directly from internal heat, emerging through fractures in a surface that had nowhere else to release its energy. Evidence of this activity lies across broad, smooth plains that differ markedly from the surrounding cratered terrain. These regions appear flatter and younger, their surfaces less crowded with impacts. They are not random deposits, but coherent expanses, shaped by molten rock that once flowed freely across the landscape. Subtle features suggest lava that spread outward in sheets, filling low areas and smoothing the ground beneath it. The lava that resurfaced Mercury behaved differently from the explosive eruptions common on Earth. With little atmosphere and lower gravity, volcanic activity unfolded quietly. Molten material seeped upward and traveled great distances before cooling, spreading thinly rather than piling into tall structures. The flows were extensive, capable of covering vast regions and burying older features without dramatic upheaval. Craters were softened or partially erased, their rims left faintly visible beneath hardened rock. This resurfacing altered Mercury's appearance profoundly. The planet became a patchwork of ancient highlands and volcanic plains, each recording a different phase of its early history. The plains testify to a time when the interior still held enough heat to melt rock and push it upward. Volcanism did not dominate the planet forever, but during its active window, it reshaped large portions of the surface at once. Over time, however, the heat that fueled these eruptions diminished. Mercury's small size allowed it to lose internal warmth more rapidly than larger planets. Without plate tectonics to sustain melting through constant motion, the supply of magma slowed. The interior cooled, pressure decreased, and fractures no longer delivered molten material to the surface. Volcanism faded not through sudden cessation, but through gradual exhaustion. As eruptions stopped, the surface entered a quieter era. Impacts continued, but there was no longer lava to erase or soften them. The balance shifted from modification to preservation. Craters accumulated again, marking the passage of time more clearly. The smooth plains became time capsules, locked in the state they held when volcanism ended. This volcanic history explains much of Mercury's stark visual contrast. The planet appears both ancient and selectively renewed, its surface bearing evidence of change that arrived briefly and then withdrew. Without plate tectonics, volcanism served as the only major agent of resurfacing, and once it ended, no replacement followed. Mercury's appearance today reflects that sequence. Fire rose when it could, spread where it was allowed, and then receded permanently. What remains is a surface shaped by limited opportunity, altered by molten rock only during a narrow window, and then left to endure. The planet's quiet plains and heavily cratered regions stand side by side, reminders that even without moving plates, a world can be reshaped, but only for a time. The space around Mercury is never still. The planet moves through a stream of charged particles flowing outward from the sun, a continuous wind that carries energy across the inner solar system. At Mercury's distance, this wind is dense and forceful, pressing directly against the surface with little interference. There is no thick atmosphere to soften the contact and no strong magnetic shield to divert it completely. The sun reaches Mercury not only with light, but with matter in motion. As these particles strike the ground, they interact with the outermost layers of rock. Atoms near the surface absorb energy and are knocked free, lifted away from the crust and carried upward. This process does not happen in dramatic bursts. It occurs steadily, grain by grain, atom by atom, as solar wind and radiation loosen material from exposed regions. Mercury's surface slowly loses what it cannot hold. Some atoms fall back, pulled again by gravity, while others escape entirely. Lighter elements are especially vulnerable, gaining just enough speed to drift into space. This exchange creates a constant cycle of loss and replacement, where the surface is both source and boundary. The planet sheds its outermost material without erosion or weather, shaped instead by direct contact with the sun itself. Among the atoms released, sodium plays a visible role. Once freed, sodium atoms gather in a thin, temporary cloud around the planet. Sunlight excites them, causing them to glow faintly. As Mercury moves along its orbit, radiation pressure pushes these atoms away, stretching them outward into a long, delicate tail. For a brief time, Mercury carries a feature more commonly associated with icy visitors from the outer solar system. This sodium tail does not remain fixed. It forms, lengthens, and disperses depending on Mercury's position and the intensity of solar activity. Sometimes it extends millions of kilometers into space. At other times, it fades into near invisibility. The tail is not made of dust or ice, but of atoms lifted directly from rock, transformed into a luminous trace by interaction with sunlight. In this momentary transformation, Mercury briefly behaves like a comet. The resemblance is not complete, but the principle is shared. Material leaves the surface, becomes part of the surrounding space, and is shaped by solar forces into a streaming form. The difference lies in the source. Comets release frozen gases as they warm. Mercury releases atoms from stone. This process reveals how deeply the Sun influences Mercury's environment. The planet is not a closed system. Its surface, exosphere, and surrounding space are connected through constant exchange. Solar wind reshapes the boundary between rock and vacuum, altering the planet not through heat alone, but through direct interaction. Mercury's comet-like behavior is subtle, fleeting, and easy to overlook. Yet it carries meaning. It shows that even solid worlds can lose themselves gradually, drawn outward by persistent forces. The sun's influence does not end at illumination. It reaches into Mercury's surface, lifts matter into space, and briefly reshapes the planet's presence in the solar system, turning rock into tail and endurance into motion. Above Mercury, the sky is not empty, but it is never complete. A thin scattering of atoms drifts close to the planet, visible only under specific conditions, when sunlight strikes them in just the right way. These atoms absorb energy and release it again as faint glows, subtle and transient. The effect is not a steady atmosphere, but a shifting veil that appears and fades with the rhythms of space. Different elements glow in different colors as they respond to sunlight. Sodium, potassium, calcium, and other atoms briefly announce their presence before dispersing. The glow does not surround Mercury evenly. It concentrates, thins, stretches, and pulls away, shaped by solar pressure and the planet's motion. What appears above the surface at one moment may be gone the next, replaced by something slightly altered. This constant change comes from how Mercury's exosphere is created. Unlike an atmosphere that circulates and settles, the exosphere is renewed directly from the surface. Atoms are released by sunlight, by the impact of solar particles, and by tiny collisions with micrometeorites. Each release event adds a small contribution, while escape and redistribution remove others. The balance never holds long enough to become stable. As Mercury moves through its orbit, the sun's influence varies. Radiation intensity changes, solar wind strength fluctuates, and magnetic conditions shift. Each variation alters how atoms behave once they leave the surface. Some are pushed outward into space, others fall back along slow arcs, returning to the ground only to be released again later. The sky is rebuilt repeatedly from the same material, never settling into repetition. The surface and space above Mercury remain tightly linked. Rock and dust are not separate from the surrounding environment. They participate in an exchange that has no clear boundary. An atom knocked loose from stone becomes part of the sky, and moments later may return to the ground or vanish entirely. This interaction happens everywhere and continuously, connecting the planet directly to the space it moves through. Because of this, Mercury does not present a fixed appearance when viewed up close. Its sky responds to time, position, and solar behavior. The planet carries an atmosphere that is always in motion, yet never accumulates. Each glow is temporary. Each tail fades. Each pattern shifts. What surrounds Mercury is defined less by composition than by process. This unsettled sky reflects Mercury's broader nature. The planet is shaped by persistence, but also by constant adjustment. It resists forming stable layers, whether of air, heat, or change. Instead, it remains exposed, responsive, and transitional. The exosphere mirrors that state perfectly, existing without permanence, rebuilding itself from the same surface again and again. Mercury's sky never fully settles because the planet itself never fully withdraws from interaction. Light, particles, and gravity continue to shape it moment by moment. The result is a world whose boundary with space remains fluid. Above the ancient, unchanging surface, the sky tells a different story, one of motion without rest, of presence without permanence, of a planet continuously rewritten at its edges. The first glimpses of Mercury came in passing, brief encounters measured in hours rather than years. Spacecraft swept by the planet at high speed, capturing fragments of its surface before gravity released them back into solar orbit. These flybys offered narrow windows, moments of observation rather than sustained study. What they revealed was intriguing but incomplete, a world half seen and half imagined from limited angles and fleeting light. Early missions returned images and measurements that hinted at complexity, yet left wide gaps. Large regions remained unobserved, hidden in darkness, or simply beyond the path of the spacecraft. Instruments were constrained by distance, speed, and the technology of their time. Data arrived in pieces, difficult to place into a coherent whole. Mercury appeared heavily cratered and dense, but much about its structure, composition, and behavior remained unresolved. The challenge was not a lack of interest, but of access. Mercury's proximity to the Sun complicates navigation and observation. Spacecraft must endure intense heat and radiation while maintaining precise trajectories in a region dominated by strong gravity. Early missions prioritized survival and basic mapping over close, prolonged measurement. The planet was studied cautiously, from afar, leaving many details beyond reach. This changed with the arrival of orbital missions designed to remain. By settling into orbit, spacecraft could observe Mercury repeatedly, under different lighting and from varying altitudes. The surface could be mapped systematically. Instruments could linger, collecting data over long periods rather than single passes. Patterns emerged that flybys could never reveal, and inconsistencies in earlier interpretations began to resolve. Modern instruments refined understanding by expanding both precision and scope. High-resolution imaging revealed subtle surface features and geological relationships. Spectrometers identified surface chemistry with greater confidence. Laser altimeters traced the planet's shape in fine detail, uncovering variations linked to internal structure. Magnetometers measured the behavior of Mercury's magnetic field continuously, capturing changes over time rather than isolated snapshots. Close observation remained difficult even then. Maintaining orbit required careful management of heat and fuel. Instruments faced constant exposure to solar radiation, and operational constraints limited when and how measurements could be made. Yet, persistence compensated for difficulty. Gradually, incomplete pictures filled in, and assumptions based on sparse data were replaced with evidence drawn from repetition and duration. What spacecraft have actually seen is not a finished portrait, but a layered one, each mission built upon the last, adding clarity while revealing new questions. Features once thought simple gained depth. Processes assumed inactive proved persistent. Mercury became less an object glimpsed and more a place observed. The transition from flybys to orbital study transformed Mercury from a distant curiosity into a comprehended world. It showed how method matters as much as discovery. Brief encounters can inspire, but sustained attention reveals structure. Even so, Mercury resists full familiarity. The difficulty of close observation remains part of its story, reminding us that understanding often comes not from first sight, but from returning again and again, slowly assembling meaning from patience and persistence. Some of Mercury's most important qualities remain hidden, not because they are unreachable in principle, but because the planet offers few ways to listen. Beneath the surface, temperatures are estimated rather than measured, inferred through models that balance heat flow, composition, and magnetic behavior. These estimates are carefully constructed, yet they remain approximations. No instrument has directly sampled the warmth deep within the planet, and the true thermal state of the interior remains partially veiled. The composition of Mercury's core carries similar uncertainty. Its size and metal richness are well supported, but the exact mixture of elements within remains unresolved. Iron dominates, yet how much sulfur or other light elements are present is still debated. These components affect melting behavior, density, and heat retention. Without direct samples, scientists rely on indirect clues drawn from gravity, magnetism, and surface chemistry, each narrowing possibilities without fully settling them. One of the largest gaps comes from the absence of seismic data. On Earth, seismic waves reveal interior structure with remarkable detail, tracing boundaries between layers and recording their properties. Mercury has no network of seismometers. No vibrations have been recorded traveling through its interior. Without these signals, the precise thickness of layers and the sharpness of boundaries remain matters of inference rather than measurement. The difficulty lies in access rather than intent. Landing and operating instruments on Mercury's surface presents extreme challenges. Temperature swings, radiation, and limited energy availability restrict what can survive for long durations. Establishing a stable seismic station requires conditions Mercury does not easily offer. As a result, the planet's interior must be interpreted from afar. In place of direct measurement, scientists assemble evidence from multiple sources. Gravity data reveals how mass is distributed within the planet, hinting at core size and density contrasts. Subtle changes in Mercury's rotation and orientation provide clues about how tightly the crust is coupled to the interior. Magnetic observations suggest the presence of molten regions, narrowing the range of possible temperature profiles. Each dataset contributes a piece, and together they form a constrained picture rather than a definitive image. Laboratory experiments also play a role. By recreating high pressure and high temperature conditions on Earth, researchers test how materials similar to Mercury's might behave. These results inform models, helping determine which internal configurations are physically plausible. Computer simulations then explore how such interiors would evolve over billions of years, comparing outcomes with what spacecraft observe today. This approach favors consistency over certainty. Rather than a single measurement answering every question, understanding emerges from agreement between independent lines of evidence. When gravity, magnetism, chemistry, and thermal models converge, confidence grows. When they diverge, new questions arise, guiding further study. Mercury remains a planet partly known through reflection rather than direct contact. Its interior is mapped through effects rather than observation, sensed through how it influences the world above. This distance does not diminish the science, it defines it. Mercury teaches that some worlds are understood not by touching them, but by patiently interpreting the signals they cannot help but send outward, revealing themselves indirectly, one constraint at a time. Seen side by side, Mercury and Earth share a basic identity. Both are rocky worlds, formed from similar materials, shaped by early heat and collision. Beyond that shared origin, their paths diverge quickly. Mercury is small and compact, with gravity that struggles to hold what Earth retains with ease. Earth's greater mass draws material inward and keeps it close, allowing layers to build and systems to persist. Mercury's lighter pull leaves it exposed, unable to gather or protect much beyond its surface. Gravity influences everything that follows. Earth's stronger gravity supports a thick atmosphere that spreads heat, circulates energy, and shields the surface. That atmosphere slows change, softening extremes into patterns that repeat and stabilize. On Mercury, the absence of a substantial atmosphere removes that moderation. Heat arrives directly and leaves just as freely. Conditions swing without resistance, and no buffer forms to smooth them into balance. Distance from the sun deepens this contrast. Earth sits in a region where sunlight delivers warmth without overwhelming the surface. Energy arrives in amounts that oceans and air can absorb and redistribute. Mercury's orbit places it much closer, where solar energy dominates every interaction. Proximity alone does not dictate fate, but it amplifies every difference. For Mercury, closeness means constant exposure. For Earth, distance allows equilibrium to emerge. Timing also played a quiet but decisive role. Earth formed with enough mass early enough to capture an atmosphere before solar radiation intensified. Liquid water could exist, further stabilizing temperature and chemistry. Mercury formed closer in, under harsher conditions, at a time when holding volatiles was far more difficult. Once lost, those early advantages could not be recovered. The planet settled into a state defined by what it lacked as much as by what it contained. Heat followed similar trajectories. Earth's interior retained warmth long enough to drive tectonics, volcanism, and magnetic protection over vast spans of time. These processes recycled the surface and refreshed the planet's systems. Mercury cooled more quickly. Its internal activity faded earlier, leaving a surface that preserved history rather than renewing it. Stability on Earth emerged through motion. On Mercury, stillness took its place. The result is two rocky worlds, with radically different outcomes. Earth became layered, buffered, and self-modifying, its surface reshaped repeatedly by air, water, and internal motion. Mercury became exposed, enduring, and precise, its surface shaped primarily by early events and slow contraction. One world favors balance through change, the other reveals endurance through limitation. Neither outcome was inevitable. Each reflects a narrow set of conditions aligned at the right moment. Mercury and Earth demonstrate how small differences in mass, distance, and timing can redirect planetary history entirely. From similar beginnings, they arrived at opposite expressions of what a rocky planet can become, one stabilized by shelter, the other defined by exposure, both quietly shaped by where and when they formed. Mercury occupies a narrow lane of possibility, a place where planet formation is tested against limits. In the early solar system, material moved chaotically, colliding, merging, and scattering under intense heat and gravity. Mercury formed where conditions were sharpest, closest to the sun's influence, offering a record of what happens when growth unfolds under constant pressure. From this position, Mercury teaches that early solar systems are not gentle environments. Heat, radiation, and rapid orbital motion shape what can accumulate and what is lost. Models that work well for planets farther out begin to strain when applied inward. Mercury shows that proximity compresses outcomes, favoring density, resilience, and endurance rather than balance or abundance. Traditional formation theories once favored smooth gradients, with rocky planets differing mainly by size and distance. Mercury resists that simplicity. Its composition and structure imply that processes near a star may strip material selectively or prevent certain components from settling at all. This forces models to incorporate extreme conditions rather than treating them as minor variations. The planet also highlights the role of timing. Accretion that occurs early, before stellar output stabilizes, may produce very different results from growth that continues later. Mercury's characteristics suggest that when formation happens under intense early radiation, the resulting world retains a distinctive imprint. That imprint persists long after surface activity slows. Mercury challenges the idea that planets of similar type must follow similar paths. Its existence demonstrates that rocky worlds can diverge sharply even when starting with comparable ingredients. This diversity expands how planetary scientists interpret observations of other systems. When dense, close-in exoplanets are detected, Mercury provides a familiar reference rather than an anomaly. By forcing theory to explain an outlier, Mercury refines the broader framework of planetary science. Models gain strength when they accommodate both typical outcomes and rare extremes. Mercury insists on accounting for loss as much as accumulation, for erosion as well as construction. It emphasizes that planet formation is not only about building, but also about what survives. Laboratory experiments and simulations now reflect this influence. Conditions once considered too extreme are tested deliberately. Formation pathways include high temperature chemistry, rapid orbital dynamics, and prolonged exposure to stellar winds. Mercury's traits guide these efforts, anchoring abstract scenarios in a real, measured world. In this way, Mercury serves as a calibration point. It grounds theory in reality, reminding scientists that nature explores every edge of possibility. The planet's quiet endurance makes it invaluable, not because it fits expectations, but because it reshaped them. Through Mercury, planetary science learns to widen its perspective, embracing complexity where simplicity once seemed sufficient. As a test case, Mercury does not offer a single answer. It offers constraints. Within those constraints, understanding grows sharper. Planet formation becomes less uniform, more conditional, and ultimately more accurate. Mercury's role endures as a guide to what worlds can become when formed under the most demanding conditions space can offer. Mercury's smallness began early, before the planet had time to become anything else. Near the Sun, space was restless. Material moved quickly along tight orbits, and collisions carried more energy than they did farther out. Instead of gently merging, many encounters shattered, scattering fragments back into the inner system. Growth here was difficult, not because material was absent, but because it refused to stay gathered for long. Accretion near the Sun faced limits set by speed and heat. Dust and rock traveled fast, pulled by strong gravity and intense radiation. Particles that might have settled into a growing world elsewhere were repeatedly disturbed, redirected, or lost. Mercury accumulated what it could, yet each addition came with risk. The same forces that allowed growth also encouraged removal, trimming mass as quickly as it formed. Loss became part of the process. Early impacts struck Mercury with enough force to eject material beyond recovery. Lighter elements were especially vulnerable. Some were vaporized outright. Others were carried away by energetic collisions that exceeded the planet's modest gravitational hold. Over time, the balance favored density over volume. What remained was not what formed most easily, But what endured? Solar radiation intensified this pattern. Close to the sun, radiation pressure and charged particles interfered with accumulation. Volatile materials were stripped away before they could settle. Even solid matter faced erosion as solar energy energized surfaces and lofted atoms into space. Growth slowed not from a lack of building blocks, but from constant interference, a steady thinning applied to every stage of formation. The planet's scars reflect this difficult beginning. Mercury's surface bears the marks of impacts that arrived early and often when the solar system was crowded and unstable. Without thick layers of atmosphere or active surface renewal, those marks endured. Each crater records a collision that altered the planet's mass as much as its appearance. The surface became a ledger of losses as well as gains. Proximity shaped everything. The sun's gravity influenced orbits, drawing objects inward and accelerating encounters. Radiation shaped chemistry and stability. Heat altered how materials behaved when they collided or melted. Together, these effects defined what Mercury could become. Not a large, layered world with abundant reservoirs, but a compact planet shaped by endurance and removal. Mercury stayed small because staying large required protection it never had. It remained scarred because change slowed early, preserving what was written in its surface. The planet's form is not a failure of formation, but a record of formation under pressure. In the inner solar system, proximity does not simply warm a planet, it reshapes its destiny, narrowing outcomes until only the most resilient structure remains. Mercury's future unfolds quietly, measured not in events but in gradual change. Deep beneath the surface, heat continues to leak away into space, following a path set billions of years ago. The planet's interior cools slowly, constrained by its size and composition. This cooling is not dramatic. It is steady, persistent, and irreversible, shaping everything that follows. As temperature decreases, Mercury's interior contracts further. The planet has already shrunk noticeably over its lifetime, and this process has not ended. Each small loss of heat leads to a slight tightening of the internal structure. The solid shell adjusts, compressing inward by tiny increments that accumulate across immense spans of time. The surface responds by shifting, forming new stresses atop ancient ones, though these changes now proceed far more slowly than before. This gradual cooling also affects Mercury's magnetic activity. The field that still surrounds the planet depends on motion within its metallic core. As heat diminishes, that motion weakens. Energy available to drive circulation declines, and the magnetic field becomes less vigorous. It does not vanish suddenly. Instead, it fades unevenly, growing weaker and less complex as internal dynamics slow. Over long durations, the field may lose the strength needed to persist at all. Without sufficient internal energy, the processes that sustain it cannot continue indefinitely. Mercury's magnetic presence will thin, offering less interaction with the surrounding space environment. Even so, this transition will be subtle, stretched across timescales that dwarf human history. Surface activity follows the same restrained pattern. With limited internal heat remaining, volcanism does not return. The crust settles into rigidity, preserving its form rather than reshaping it. Impacts will still occur, but far less frequently than in the early solar system. Erosion remains minimal. The planet grows increasingly quiet, its major transformations already behind it. This future does not imply disappearance or decay in the usual sense. Mercury does not break apart or fall silent all at once. Instead, It approaches a state of equilibrium defined by low energy and minimal change. Processes that once acted more rapidly now operate at barely perceptible rates. The planet persists, but with fewer internal interactions shaping its surface and environment. In this inert state, Mercury becomes a record not only of the past, but of planetary aging itself. Its long future mirrors its long history, dominated by endurance rather than renewal. The same factors that limited its growth also ensure its persistence. With little to lose and little to gain, Mercury remains largely as it is, slowly releasing the last of its internal energy into space. Time continues to pass, and Mercury continues with it, shaped less by events than by duration. Cooling, contraction, and fading magnetism do not bring an ending, but a settling. The planet moves towards stillness, not abruptly, but with the same quiet persistence that has always defined it, becoming ever more inert while remaining entirely itself. Mercury's importance does not fade with distance or time. Though small and quiet, it holds lessons that extend far beyond the inner solar system. As astronomers discover planets orbiting close to their stars, Mercury offers a familiar reference. It shows how rocky worlds behave under intense radiation, high orbital speeds, and constant stellar influence. What appears extreme in distant systems has already unfolded here in a form we can study closely. Planets found near their stars often appear dense, compact, and stripped of volatiles. Mercury demonstrates that such traits do not require exotic origins. They can arise naturally from formation and evolution under strong stellar conditions. Its history helps interpret these distant worlds not as anomalies, but as expected outcomes of proximity. Mercury provides a physical example that grounds theories applied to faraway systems. Beyond exoplanets, Mercury deepens understanding of planetary diversity. It reminds us that similarity in starting materials does not guarantee similarity in results. Rocky planets span a wide range of states, shaped by timing, location, and mass. Mercury occupies one end of that spectrum. Earth occupies another. Between them lies a continuum of possibilities rather than a single template. Mercury expands that range, ensuring that models remain flexible rather than narrow. Extreme worlds clarify fundamental processes. By observing how Mercury responds to heat, radiation, and limited gravity, scientists refine how these factors interact elsewhere. The planet isolates variables that are blended together on more complex worlds. Its lack of atmosphere, rapid temperature changes, and exposed surface simplify certain interactions, making underlying physics easier to trace. In this way, extremity becomes a tool rather than a complication. Mercury also reshapes how planetary success is defined. It did not become layered with oceans or sustained surface renewal, yet it persists intact. Its endurance challenges assumptions that equate complexity with stability. Mercury shows that longevity can take many forms. A planet may remain viable not by adapting continually, but by losing little once its major changes are complete. As a boundary case, Mercury marks the edge of what rocky planets can withstand. It sits close to thresholds of heat retention, atmospheric loss, and internal activity. Crossing those thresholds would lead to very different outcomes. By existing just within them, Mercury helps identify where those limits lie. It defines conditions under which planets remain solid bodies rather than transitioning into something else. Calling Mercury an outlier understates its role. It does not sit outside planetary norms. It defines part of them. Its characteristics bracket what is possible, constraining theories that might otherwise drift toward oversimplification. When models can explain Mercury alongside Earth and Mars, confidence in their broader applicability grows. Mercury still matters because it anchors planetary science at an edge. It ensures that extremes are included rather than ignored. Through its quiet persistence, Mercury continues to inform how planets form, evolve, and endure, not as an exception to be set aside, but as a necessary reference for understanding the full range of planetary outcomes. Mercury remains where it has always been, close to the Sun, bearing the consequences of that position in every layer of its existence. Its story is not one of sudden catastrophe or dramatic transformation, but of steady pressure applied over immense spans of time. Proximity shaped its path from the beginning, defining what it could gather, what it would lose, and how it would endure. Nothing about Mercury is accidental. Each trait reflects the quiet persistence of conditions that never relented. Time worked differently here. Heat arrived early and stayed dominant. Material was stripped, altered, and compacted before gentler processes could take hold. What remained was dense and resilient, capable of lasting once the most violent phases passed. Loss did not weaken the planet, it refined it. Mercury became smaller, heavier, and more precise, carrying only what could survive unshielded beneath an intense star. Across billions of years, change slowed, internal motion faded, surface renewal ceased. The planet settled into a long stillness, preserving evidence rather than erasing it. This endurance does not suggest perfection or failure. It reveals a different outcome, one shaped by limitation rather than abundance. Mercury shows what a world becomes when balance is never granted, only persistence. Understanding such extremes reshapes perspective. Worlds like Earth feel stable in part because their contrasts are less visible. Mercury strips those comforts away. By examining how it behaves under relentless exposure, scientists clarify which conditions foster equilibrium and which prevent it from forming at all. Balance becomes easier to recognize when its absence is fully understood. Mercury also reminds us that planetary stories need not resolve neatly. Some worlds are not puzzles to be completed, but records to be read with care. Not every detail can be measured directly. Not every process leaves a clear signature, yet enough remains to outline the arc of history with confidence. Mercury is not solved in the absolute sense, but it is understood within the limits of observation, experiment, and inference. In that understanding lies its quiet power. Mercury anchors the boundary between possibility and loss. It marks how close a rocky planet can form, how much it can lose, and still remain intact. It shows that endurance takes many forms, some loud and active, others silent and still. As the solar system continues its slow evolution, Mercury will change little. Heat will fade further, motion will diminish. The planet will persist, much as it is now, a compact reminder of how beginnings matter. Its surface will remain etched with history. Its form will continue to reflect the environment that shaped it. At the edge of endurance, Mercury waits, not dramatic, not welcoming, but precise in what it reveals. Through it, the extremes become legible, and through those extremes, balance elsewhere becomes clearer. The smallest planet leaves a lasting impression, not by demanding attention, but by quietly showing what happens when a world forms where limits are never distant.